Section 2.4, Limits and Continuity. First, we discussed some continuity and discontinuity, definitions and description, and then we discuss continuity and elementary functions. That's something that helps us to basically recognize continuous functions easily, and it also helps us with limits. And so some people describe continuity as uninterrupted flow. A function is continuous at a point if the limit and the actual value align at that point, or the prediction, as we discussed in the past, the prediction, which is the limit, is going to match and be equal to the actual value of the function at the point. So a function f is continuous at the point c and f of c on the graph if limit as x approaches c of f of x is equal to f of c. So left limit has to exist, right limit has to exist, and they have to be equal to each other and equal to the value of the function at that point. So, and if you, again, let's repeat this, to limit it, if the function is continuous, then at point c, then the limit at c, that is limit of f of x as x approaches c, exists. The other one, that means that the actual value f of c exists. And then and there is a value L where the limit as x approaches c of f of x is equal to L, and f of c, the value of the function, is equal to f of c, basically. And so the prediction is a number, and it's equal to the f of c. Okay, discontinuities. So we kind of discussed when we were discussing limits that if a limit doesn't exist in certain places, and let's say the vertical asymptotes were some of them, and were a type. Any vertical asymptote was a type that the limit didn't exist. Any breakage would cause the limit not exist. But then there was these holes over here, and limit existed there, but it just, we didn't know how to name them. Now we have a word for it. See, the limit exists, but the value is not equal to limit. That means that it's discontinuous. So now we have a wider basically description. When we say discontinuous, it's a little bit more than just non-limit existing. So let's say this hole at this point to be A, the breakage and the jump, B, and then here the vertical asymptote C. And so let's describe the three types of discontinuities. One is the removable, that's a hole. The limit exists, but it is not equal to the actual value, and that's A. And so the limit of f of x as x approaches c, it exists, but it doesn't equal to f of c. B is jump, and that's when one-sided limits are not infinite, and the two-sided limits does not exist. And so that's that's a form of discontinuity, basically, also. And the third type of discontinuity is the infinite discontinuity. Either one-sided limit approaches infinity, or either one or both of them approach infinity. Both counts as infinite discontinuity, basically. And so let's talk about one-sided continuity. If left continuity means limit as x approaches c from the left of f of x is equal to the value of f of c. Right continuity is limit f of x as x approaches c from right side is equal to the value of function at c, f of c. So let's do example 1. Identify any points which are left or right continuous only, and identify and classify all any discontinuities. So over here, when I'm looking at this, the discontinuities are at x equal to 1, x equal to 3, and x equal to 5. And so at x equal to 1, we have basically, let's see, at x equal to 1, and the left-sided limit is equal to 3, equal to value of the function. So we have a left-sided left continuity there. At x equal to 3, we have neither side continuity, but both left and right limit exist. At x equal to 5, there is a right side limit exists, and it's equal to the value of the function. So we have a right side continuity, right continuity. And so we have at point 3, we have neither continuities. At point 1, we have left continuity. At point 5, we have right continuity. And so what are the type? All 3 of them are actually jump continuity. So, excuse me, all 3 of them are jump discontinuities. So jump discontinuity at x equal to 1, 3, and 5. Example 2, continuity and discontinuity. So this time it's slightly different from the previous slide, and you can see we still have over here at x equal to 1, and the function is left continuous, and so the limit as x approaches 1 from the left is equal to 2, and the value of the function is equal to 2, but still a jump discontinuity. At x equal to 3, and we see that both limit from left and limit from right exist, and they are equal, but they're not equal to the value of the function at 3. So the limit at 3 as x approaches 3 is 4.5, but the value of the function is 2.5. This one is a whole discontinuity. And then the limit as x approaches 5 from left and right, they exist, but they're different, And f of 5 is not defined at all. You don't see any value for f of 5. This is still jump discontinuity. So 2 jump discontinuities at 1 and 5, and a whole discontinuity at x equal to 3, and only one of them is one-sided continuous, left continuous at x equal to 1. Let's do one more example. In here, you see that at x equal to 0, there is a infinite discontinuity, and x equal to 2, there is a whole discontinuity. And at x equal to 0, it's right continuous. At x equal to 2, it's neither left or right continuous, and limit exists though. So all these discussions, and we're really relying on the basically the graph of the function to find out whether or not the function is continuous. This information on this page gives you a lot more ideas about functions and continuity. An elementary function is a function of one variable, which is the composition of a finite number of operations, plus, minus, times, divide, quotient of exponential logarithms and constant polynomial trigonometric functions, inverse trigonomic functions, and roots. So any of these functions, if you use the function operations and in composition of the functions, or plus, minus, times, divide, you end up with an elementary function as well. So now the important part is the big information in here. Elementary functions are continuous on their domain. So you don't have to check. If you don't know the rule of the function, you don't know if it's continuous, then you have to check. But if you have, you don't know if they're elementary, then you have to check. Or if you have the rule of the function and you don't know, but they are not elementary functions, which we give examples right away, then you have to basically check. But within their domains, they are always continuous. And so the points that are not in the domain, they are not continuous. And so in here, for example, f of x equal to log base 5 of x squared plus 3 minus e to the power sine of x, even though it's very complicated looking, it's still an elementary function, right? And so a logarithm, the domain of a logarithm is when inside is bigger than 0. Strictly bigger than 0. And in here, x squared plus 3 is always bigger than equal to 3, and therefore there is no problem with this part to make the restricted domain. There's no problem here to restrict the domain. F of x is defined on the entire real numbers, and f of x is an elementary function, so f of x is continuous on all real numbers. And so what about g of x? With g of x, you have a little bit more stuff going on. One thing you have to check the denominator, whether or not denominator is 0, to exclude the denominator, and then you have to check where sine of e to the power x is negative, and then exclude those, and then you come up with values that are the domain of g of x. And then g of x, since g of x is an elementary function, when you find the domain, then g of x is going to be continuous on that domain. Finding the domain of g of x is a little bit more complicated, basically, than the other function. Now, let's follow some of the rules that we have that are kind of corresponding to the limit laws. So find some laws with continuity. If f of x and g of x are continuous at x equal to c, then a constant time f of x is also continuous at x equal to c for any constant k, and then f of x plus minus g of x, either one, is continuous at x equal to c. F of x times g of x is continuous at x equal to c, and f of x divided by g of x is continuous at x equal to c, provided that g of c is not equal to 0. So it's continuous at points that both functions are continuous, minus the points that make the denominator 0. So basically, every act that we need to do to construct the elementary functions from functions that we know and are continuous, make the functions continuous. And then finally, if f of x is continuous at x equal to g of c, then f or g of x is continuous at x equal to c. So the laws that we explain right here, and plus the fact that with the simple information about continuity of, let's say, simple trig function, simple exponential e to the x or b to the x function, and log of x function, and that sort of thing, with those information, if you actually use those, because those are all continuous, so any operation on them also give continuous function out. And if you look out carefully, you see that you're basically excluding whatever is not going to be in the domain. And so this is the explanation that you need why the elementary functions are continuous. Okay, now that we explained why we basically made sense of why elementary functions are continuous, we want to talk about the domain. So first, polynomials are continuous at every real number, because that's the domain of polynomials. Even root functions are continuous at every positive number. Odd root functions are continuous at every real number. Logarithms are continuous at every positive non-zero number. Exponential functions are continuous at every real number. Sine of x, cosine of x are continuous at every real number. Tangent of x, secant of x are continuous everywhere except for pi half plus n pi, and that was the discussion that we had in the previously that we discussed, where the denominator is equal to 0 is not going to be part of the domain of tangent of x and secant of x. And then cotangent of x and cosecant of x are continuous everywhere except for values 0 plus n pi or k pi, either one would work. I click at question 1. You decide